Welcome to Wireless Future. I'm Emil Björnsson, and as always, I have Eric Larsson on the call. How are you?
Oh, hi Emil, I'm good, thank you. Been looking forward as always to recording podcast with you. So today's 27, is it?
Yes, it's episode 27, and this is an episode where we have a guest with us. So it's Florian Kaltenberger from Eurocom, where he's an associate professor and also a board member of something called the Open Air Interface Alliance. So, Florian, how are you?
Hi Emil, hi Eric. I'm very well, thank you. I'm really happy to be in the show. I'm a big fan. I listen to the podcast in my car on the way to work. So thanks for having me here.
Yeah, and thank you for listening, and to all the other people who are listening. We're happy that people are finding ways of listening to us as part of their daily life. So, as I was indicating with this open air interface, I was thinking that this episode would be dedicated to air interfaces in general. So, let me kick this off with a question for you, Florian. What is an air interface?
Well, the air interface is simply let's say the last mile of your mobile network. So it's the link between your base station, between your antenna and your mobile device. Yeah? And typically that's something that is standardized. Has been standardized since 2G basically, and different generations bring different technologies. So, for example, in 2G, it was GMSC, that was the air interface. 3G had wideband CDMA, 4G had OFDM, and 5G again is OFDM.
So there are then different types of air interfaces, and if there are like two air interfaces with OFDM, are they the same, or there are multiple different standards to care about?
No, so there is nevertheless a big difference between 4G and 5G. I mean, both of them are based on OFDM, but there are significant differences such that a chip that can do 4G does not necessarily know how to do 5G. The other way around might be possible, because 5G in many ways is an extension to the 4G air interface.
So, I mean, you mentioned modulation here, right? Like OFDM, but does the air interface also consist of like other components, like multiple
absolutely.
access and random access and so forth? I mean, is it a correct understanding that the air interface is everything that happens, like, well, at the access point, or I mean, the bits come in packets in some form, right? And then they are converted onto waves that are sent over the ether, and the air interface really comprises everything there: modulation, coding, random access, and so forth. Is that like an accurate definition?
Yeah, of course. I mean, there are multiple layers, even in the radio access network. So typically you have the PHY layer, the physical layer that takes care of the modulation and coding. Then you have the MAC layer that takes care of multiple access between different users, and also multiplexing between uplink and downlink. And then you have even some more layers on top, like the RLC, that also has another layer of retransmissions, and the PDCP, which is then the interface to the core network. So all of these layers, of course, work together to ensure that you have a reliable link on the radio interface.
So are all the components of the air interface standardized? I mean, if we take 5G as an example, is everything in there in the standard, or are there parts that are left to the implementation that the vendor can decide freely?
Absolutely, there are certain parts that are not described in the standard, that are actually not needed to be described in the standard. So let's take, for an example, the channel coding. Yeah, in 5G, In 5G, this is LDPC, low density parity check coding. So the standard simply describes how to encode your data. Yeah? So and this is basically everything you need to know. Then it's up to the vendor, to the chip maker, to find an algorithm that implements that an efficient decoder. That with a low error probability and with low energy consumption. So these parts are typically not described in the standard.
Right, but are performance requirements standardized? I mean, I understand that the choice of decoder isn't, or the particular algorithm isn't specified in the standard, but does the standard specify something like, well, you got to be able to decode this code with this SNR and at this error probability or anything like that?
Yes, absolutely. So that's there are plenty of documents that specify these performance requirements. So 3GPP, who is the organization who does the standardization, they even provide you with channel models that tell you exactly. So in this and that condition, so with that channel and that SNR level, you need to be able to achieve 70% of the peak throughput for this type of modulation encoding scheme.
So it's really like the standard tells you what you must be able to do, but not necessarily how to do it.
Exactly. Yes. The standard also specifies, so that's actually new in 5G, the minimum amount of receive antennas that you have to put in your handset. Well, no, I think it was already for 4G they put 2 antennas, and for 5G this is now 4 antennas. So these performance requirements, of course, take that into account. So you have to be able to achieve that with this amount of antennas, but nobody tells you you can put more antennas in the handset if you want to have even better performance than required.
So you are involved in this Open Air Interface Alliance, which has a tagline 5G Software Alliance for Democratizing Wireless Innovation. So what do you mean with that tagline, and what is the alliance all about?
Well, so Open Air Interface, so the emphasis is on the open, is actually an open source project. Yeah, so and it has been around for a while now. So it started even before I came to Eurocom, and back then, so that was before the 2010s, before LTE. It already implemented 3G radio access. So you were able to simply using our code and using off-the-shelf equipment like PCs and software-defined radios, you can set up your own base station or even a complete network that is compatible with commercial handsets, and thus have a testbed or even a functional network to do experimentation, and this continued. So ever since the beginnings, Open Air Interface has implemented 4G LTE. This was actually our first big success, because that was when we had a complete chain that was compatible with commercial equipment. And since a few years, we also have 5G, both 5G non-standalone and standalone. So yeah, and as I said, the emphasis is on open, because traditionally these systems are closed. Yeah, so I mean the big companies that sell equipment to mobile network operators, their revenue is based on patents, essential patents they have in the standard. So I mean they don't want to open up their algorithms. They don't want to show what they have inside, and that's how they make the money. Okay, but that was always a big burden for academia and research, and that was the motivation why back then my colleagues have started to provide an open source implementation of this air interface, so that other people can come and take it and get an easy entry into this systems and start setting up test beds and do research.
So then, in addition to Eurocom, which is obviously a partner in this alliance, you also have some other sponsors and contributors. Who are they, and what are their sort of roles or interest in this project?
Yes, absolutely. So a few years back, I think it was 2014, we started to set up. So when the interest really increased, Eurocom was in a difficult position, and then we couldn't manage all the requests and all the activity around it anymore. So we created this alliance called the Open Air Interface Alliance, which is a non-profit entity which is founded by Eurocom, but which is basically apart from Eurocom. And this entity is a so-called endowment fund. So it is allowed to receive donations, and these donations allow us to hire a team of engineers to be able to and managers to be able to maintain the code, to make sure that contributions to the code fulfill certain quality requirements. We have a certain quite a sophisticated continuous integration process, meaning that there is testing for every code that is contributed. There's testing, and so there are a lot of companies who have interest in having such an organization running and ensuring the quality of the code. And for example, so we have strategic members. If you allow me, I would like to list them.
Yeah, please.
There's Orange, so the mobile network operator Orange. There's Fujitsu, equipment manufacturer. There is Sequence, another chip manufacturer here in France. We also have Qualcomm. Quite happy to have Qualcomm on the board, who is quite a leader in making chips for 5G handsets. We have Meta Connectivity, so formerly known as Facebook. We have Xilinx, the makers of FPGA. And another entity that is maybe not so well known, which is called Power, the Platform for Advanced Wireless Research, which is an organization in the United States to build next generation advanced wireless platforms.
That's a rather wide array of partners, quite impressive indeed. So just so that our listeners and also I will understand this properly. So Open Air Interface is mainly software, is that right? Or do you also develop hardware? I mean, I think you mentioned that you could run Open Air Interface on like pretty much any set of PCs and SDRs or software-defined radios, but is Open Air Interface the software only, or does it also have like hardware components that come with it?
So Open Interface is only software. So what the alliance only manages the software package. But of course, to run Open Interface, you need hardware. You need typically it runs on software-defined radios.
Right, and but I mean, what are the requirements on the hardware? Could anyone like download Open Air Interface and just install it onto some appropriate? If you got some PCs in the garage and maybe some software-defined radios, and if so, what sort of software-defined radios do you need? I mean, is it like you can buy from many vendors, obviously,
yes.
but there are a few that dominate the market, I think, for like academic and experimental research, right? You can buy like off the shelf. So could you run open air interface on those, or would you need like more specialized gear here?
So yes, you can buy these devices on the internet. So the most popular software-defined radio that is used with open interface is the so-called USRP that has been designed by Ethos and is now distributed by National Instruments. And I mean, there are multiple generations of these devices, and depending on the generation you want to use, you have different requirements on the hardware. So for 4G, you can use one of the older ones, for example, the B210s, whereas for 5G, which requires larger bandwidths, you would need to use one of the more recent N310s.
But really, it's like, I mean, if you buy, in principle, I mean, you could set up your own little 5G network that would be completely compatible with all the commercial handsets and other commercial equipment by buying a bunch of these USRPs of the latest model and downloading and running the open air interface from your website. Is it like that?
Yes, it's more or less that. I mean, there are a few other small pieces that you need. You need antennas, and depending on which band, which frequency range you want to do, you might need other equipment. So, for example, if you have TDD, then typically you need a front end that switches between uplink and downlink, or in some cases a circulator would do too. Whereas in FTD, you might need an additional duplexer to have a better performance on the radio level.
Yeah, I certainly understand. I mean, that there might be auxiliary hardware components required that don't come as standard supplies with the USRPs. But in principle, I mean, you could buy these components off the shelf and a bunch of USRPs, and then just set up and run.
Exactly. Yeah. I mean, you have, of course, also some requirements on the computing hardware. I mean, maybe the laptop that you have lying in your garage won't fulfill those requirements anymore. So you need a bit of a PC that is more up to date.
Right.
But yes, I mean, in total, I think for a few thousand euros, definitely less than 10, you can set up your whole 5G system.
Wow, that's quite amazing indeed. So what programming languages are used here? I mean, how is open air interface implemented?
So I would say 99% is C, so classical C, because we do try to optimize our code as much as possible, and we do actually rely a lot on a specialized instruction set that you have on basically on every modern chip. So we use this vector processing instructions, SSE and AVX, because otherwise you would never be able to run this thing in real time on a classical computing infrastructure.
So you mentioned earlier that for the conventional vendors, patents is a big thing for getting revenue. So if I would now download and buy all this stuff that you mentioned, can I just, and I would get the license, of course, for Spectrum, can I just run it, or do I need to get an agreement when it comes to licensing patents from the big vendors, or how does it work?
Very good question, thank you. So one of the contributions from Open Air Interface is also the Open Air Interface open source license. So classical open source licenses basically are not compatible with patents. So when you when you own a patent and you decide to implement the technology in open source and give it out in open source, basically you lose your rights to your patent with classical open source licenses. But we basically at the Open Interface we wanted to merge both worlds, and we created this Open Interface license that allows you exactly that. That allows you to have a patent, implement it in open source, and still be able to ask for royalties for your code. But that only comes into play when you start using open interface commercially. Yeah, so when you go out there and make a product, for example, a base station that has open interface inside, and you sell this on a large scale, then it would be your responsibility to go to 3GPP and figure out how to pay your license fees to the other big players. As long as you use open interface just for your own research and in the lab, and this is explicitly mentioned in the license, you don't need to worry about that. Yeah, so you can use it freely in your own research without having to pay any fees. Of course, as you said before, you have to make sure if you want to use it outdoors or with, let's say, significant power, that then you have to make sure you have a license for the frequency that you're using, because keep in mind that 3GPP systems, or at least the classical 3GPP systems, don't work in unlicensed spectrum, so they only work in licensed spectrum. So you need a license.
So how advanced are these, test beds that you can build using our open air interface, and particularly perhaps the test beds that you are building at Eurocom? Do they support massive MIMO, for example, with lots of antennas, or put it this way, how many antennas can you equip your test bed with and still run it with open air interface?
Yeah, so of course there are limitations. To the approach. So having to run everything in software makes the entry barrier lower, but of course it is more complex, and so we can't achieve the same level of performance as you would have with a commercial equipment. But we do support MIMO. We have for 4G we support up to 2 times 2 MIMO. For 5G. Right now we have 2 times 2 MIMO, but going on to up to 4 layers. We had projects, and that's about as many antennas as we have also deployed here at Eurocom in our testbed.
So you aren't, if I understand this well, you aren't really at massive MIMO yet, right? You said 4 streams or 4 antennas is quite far from like maybe 64 or like 100 antennas.
Well, but keep in mind that the number of layers is not the same as the number of antennas. So,
sure.
we did have a project where we did massive MIMO. We had an antenna array of I think it was 64 antennas. And we were doing experiments of using channel reciprocity for massive MIMO. So that we have done in the past. That was, I think we managed to do up to 2 streams. So we were able to serve 2 users in parallel with this massive MIMO testbed.
Mm-hmm. Yeah, I think that was my real question. So if I got you right here, you said 64 antennas, but only 2 streams.
Exactly.
Through spatial multiplexing. Right, and that is with TDD, fully digital reciprocity-based beamforming then? Yes.
At the time, it was that, yes.
So where's the bottleneck here? What prevents you from? Well, 64 antennas is still a lot, right?
Yes.
Well, you could benefit from more. You can never have you can never lose by having more antennas, let's say.
Yes.
But where's the bottleneck in terms of supporting more streams? If you were to go to multiplexing 10 or 20 terminals at a time with open air interface, is it just that, a standard PC that runs the software, even though your algorithms are coded in C and so forth, they just aren't efficient enough to deal with all the data? Or could you shed some light on that?
Yes. So there are 2 bottlenecks. If you implement your massive MIMO system, a fully digital massive MIMO system, where you have every antenna is basically connected to an RF chain, you basically it's actually not a problem to set up a testbed to connect multiple SDRs together to have this kind of massive array. The problem is streaming all the samples into the host and processing all the sample into in the host. Yeah? Because first of all, it's a massive amount of data. So even for LTE 20 megahertz, if you have 64 channels, that's many gigabytes per second that you need to stream into the host PC, and then you need to process.
That's a lot. That's exactly a lot, yes.
So that's the first bottleneck, and then the other bottleneck is on the number of layers. So of course, the more layers you have, so your throughput or your channel, your throughput basically depends on the number of layers. And since we do everything in software, even the channel decoding, so then the channel decoding basically becomes the bottleneck. We can't. Today, if you run the LDPC decoder in software, basically the maximum throughput that we can get is a few hundred megabits per second. And then, but that bottleneck could be overcome by techniques like offloading the channel decoding to dedicated hardware. Yes. There is dedicated hardware, FPGAs or others, that you can offload the channel decoding to. So that bottleneck could be overcome.
And, yeah, certainly. I guess you could use hardware accelerators or offload some of the computations onto supporting other machines, or even just cut the bandwidth. If the goal is to demonstrate the use of many antennas, you could reduce on the bandwidth, and that would cut also the amount of data you have to process.
You could do that too. You could do that too. Or the third option is also to and that's something we have been started to try recently, to use the technologies that have been specified by the O-RAN Alliance. So to use a fronthaul instead of streaming the IQ samples basically one-to-one uncompressed to the host. You could do a little bit of processing in your radio unit, for example, the OFDM front end, that allows you to compress the data that actually goes into the host, and then you could process more antennas in the host.
Mm. Yeah, I always like to think that you probably want to move as much of the processing to as close as possible to the antennas, right?
Yes,
but
yes.
At the same time, my impression has been that the philosophy behind open air interface, that you collect all the data to like a central place in a PC, and then you do all the number crunching there, and this just makes it somehow. I understand, the computational challenge when you have a lot of antennas and high bandwidths, but in principle you can run everything on a single machine, right? With efficient code written in C, and then but even so, you'll at some point hit the wall in terms of how much bandwidth you can support and how many antennas you can support and how many streams that you can multiplex and so on.
Yes.
Yeah, so great. Mm.
So it seems like this open air interface was very early with sort of using general purpose hardware. You mentioned already in the 3G era, and now there is a lot of talk about C-RAN or Cloud RAN, that you would be sort of splitting up and using general purpose hardware instead of dedicated hardware for different kind of things. So now when sort of bigger vendors are actually supporting these type of things, does that make the sort of open air interface approach less relevant, or?
No, quite the opposite actually, because that increased the interest in open interface, because we were one of the first ones that actually proposed this approach to do everything in software. Before, it was long before people started to use the term Cloud RAN or virtualized RAN. And this is one of the reasons why open interface became so popular, because people see it as a tool for Cloud RAN. And I remember one of the first basically use cases of open interface that was done completely outside of Eurocom was a demonstration by, I think it was China Mobile at one of the Mobile World Congresses, where they showed a Cloud Run demo that was based on OpenInterface. That was I'm trying to remember, but that was definitely more than 5 years ago.
Yeah, I think they were sort of publishing some papers about that they wanted Cloud Run almost 10 years ago or something like that.
Yes. And they were using OpenInterface as their first proof of concept for this. Huh?
Yeah, so returning, I think you mentioned earlier, this Open Run. Could you elaborate a little more on like the relation,
yes.
or how could Open Air interface benefit from Open Run, or vice versa, or how do you see the relation there, and how do you see that particularly playing out like in the long term?
So Open Run, let me just quickly explain, is a kind of evolution of this Cloud Run concept, and basically resulted in another organization called ORun, simply, which produced a set of specifications that kind of standardize the architecture of an Open Run network. And the key concept here is that they introduced a set of interfaces within the existing specification of 3GPP that allows you to separate certain functionality within the radio network, and that further allows you to basically run most of the components of a radio network on general purpose hardware in a virtualized infrastructure. And as I was saying before, I think the concept of Open Run, together with open source software like OpenInterface, is the perfect marriage. Yeah? So they perfectly go together, because OpenInterface basically delivers the software that allows you to run several components of an Open Run architecture in a virtualized environment. Yeah, but it's not the same thing. So the open in Open Run does not refer to the same thing as open in the OpenInterface. So the open in Open Run refers to the open interfaces between the different components. The different components could still be closed. Whereas in OpenInterface, it's really the software is open. So if you put the two together, you have basically a double open system.
Yes, but that's an important distinction, right? I mean, yes. Open here means different things in the two different terms. Yes,
exactly. Yes.
Yeah, and if I understood correctly, one of the goals with Open Run is also that you should be able to more easily buy different pieces of equipment from different vendors and know that they can operate well together.
Exactly. Yeah. So as I said, they try to reduce the amount of specialized hardware that you need. So basically, in an Open Run network, the only specialized hardware that you need is the radio unit, and which is then connected over frontal network to what is called a distributed unit and a centralized unit, and both distributed unit and centralized unit can be run on software in a virtualized environment. So it's basically a network function. And you could have you can buy this network function from one vendor and maybe the other network function from the other vendor, and if they both adhere to the Open Run specifications, they should work together.
So when it comes to Open Run, the thing that I come across mostly in my research is something called functional splits. Mm-hmm. And I think you were essentially talking about that a few minutes ago when you said that we can choose where we do the multi-antenna processing. Is it close to the antennas or is it at a centralized point? Maybe you can take an opportunity to explain what is a functional split and why are there like 5 different ones in O-RAN?
Yes. So a functional split means that basically you cut the protocol stack of a classical base station, a GNOT-B, into several functions with well-defined interfaces in between. And indeed, at the beginning, when Cloud Run, when these concepts were being discussed, there were a multitude of different functional splits that are available, and so only at the end only a few of them I would say are being used. So one of them is the split between the radio unit and the so-called distributed unit, which is in O-RAN called the 7.2 split, which means that you do the OFDM processing, so the FFTs and the IFFTs in the radio unit, and only send the basically the subcarriers that carry data, the non-zero subcarriers. You send them over the fronthaul to the distributed unit. And then the other split that there is in O-RAN is the F1 interface, which is the split between the distributed unit and the centralized unit. And as the name suggests, the split has been chosen such that these units can be geographically distributed differently. So you would have maybe a distributed unit function you would have close to the edge, so close to the actual base station, because all the time sensitive processing happens in there. And then you have a centralized unit which doesn't do that much of a time sensitive processing, which has more of a control function, which could be in a data center which is far away from the edge, or could not. Yeah, depends on your application. So the functional splits allow you to adapt your network structure to the application. Yeah? If you want really low latency, then also on the user plane, then maybe the centralized unit is also on the edge, and you have an application server right on the edge. Or if you want to just mobile broadband without low latency and for things like Netflix or others, then your centralized unit might be in the core or further from the edge.
So I think when it comes to this MIMO processing that we talked about before, if I understood correctly, there's like one split where you from the antennas will have to send, if you have 64 antennas, you need to send 64 streams of parallel data down for further processing, while there's another split where if these 64 antennas only carrying 4 layers of data, you only need to send 4 layers. Yes. Because you sort of do that mapping.
Yes, yeah. So that's possible too. That's part of the O-RAN specification that beamforming and or pre-coding could also potentially happen in the radio unit, exactly for that reason. So that instead of having to transfer 64 the IQ samples of 64 antennas, you only transmit the IQ samples of your 4 layers. And the beamforming and the pre-coding is happening in the radio unit. Mm. Yeah.
So it offers considerable flexibility in terms of where the different operations are performed, and in terms of what data that is actually shuffled around on these different front hauls and interfaces. Then.
Yes, exactly. It simply gives you great flexibility to deploy your network for different scenarios.
Mm-hmm.
I mean,
yeah. So I'm trying to summarize what I've come to understand about the philosophy behind open air interface here, and so one thing is the openness, right? The fact that you can download as open source the software and run it more or less on any equipment, assuming it's like modern enough and the other philosophy, if I understand well, is that open air interface should run on general purpose hardware.
Mm-hmm.
So aren't there like drawbacks and risks to that? I mean, one could be power consumption, obviously, but I'm thinking more in terms of where the boundaries are in terms of what you can actually achieve and what you can actually demonstrate. I mean, we talked earlier about like how many layers you could support and how many antennas you could support, and at some point, I mean, just the fact that you're running everything on a PC and the CPU processing capability will be the limiting factor. Do you see here that you in the future would build like ASICs instead, or FPGA, or use FPGAs, or do you in any way, let's say in retrospect, regret a little bit that, well, we should have built this using a rack of FPGAs rather than running it on a off-the-shelf PC? No. Or could you comment on like how you see that, both in terms of the history and also for future development?
No, first of all, there are absolutely no regrets. I think the choices that we made were were good, because one of keep in mind, the open interface was started by the research community and for the research community in the first place, and we still we still value that a lot, and this is still important for us. And having things also, having things on the FPGA is nice and good for certain applications, but in general the code needs to stay flexible, we need to be able to adapt to changes in the standard easily. And I also don't think it's open interface is not let's say the savior of all of all mobile networks. So there are limitations, and I don't think that big mobile operators like Orange would all of a sudden change the whole network to use open interface. That, as you said, will not be energy efficient. But there are use cases, and especially with 5G, a lot of these use cases are popping up, where where this approach is interesting. I mean, think about private networks. When 5G was designed, people said we need networks for different use cases, and a lot of them were private use cases. For example, a factory floor where you have a lot of machinery that needs to connect to the network, or campus networks, and here one of the main drivers is simply the cost. Building a private network with the same equipment that you see in national networks is prohibitively expensive, and there's a real market opportunity also for open interface to provide a solution, and build a private 5G network, maybe even on existing infrastructure. I mean, for example, here at Eurocom we have plenty of servers in our server room that can run some of these functions of our mobile network.
So in principle, are you suggesting that one could set up a private 5G network by downloading the open air interface and buying appropriate off-the-shelf hardware, and then just run it? Is it like stable enough for that? I mean, if you have
we're getting there. So I haven't seen larger or networks with more than 2 base stations that run open interface. But there are several ongoing projects that actually have this goal. And there are even some startup companies that try to build products based on open interface to fulfill exactly that gap, to provide equipment to build private 5G networks. And I think in a few years from now, maybe 2-3 years from now, we will see. I'm positive that we will see such networks.
Is that your long term? I mean, you said earlier that open interface was developed by researchers for researchers, right? And I understood that one of the goals was to also lower the barrier in terms of what you need to get started with experimental research and actually building a test bed, which is even 5G compatible here then. But really supplying software for like commercial operation of a private 5G network is something else, right? So
yes,
where on that scale do you really position yourself, and how do you see open interface developing in the future in that regard?
So personally, I'm a professor at Eurocom, so my business is research. But so and I will keep on using open interface for my research. But I absolutely see a potential for open interface to be used in commercial products, and it is one of the goals of the alliance to foster that, to foster an ecosystem, and to support startups who want to build such products. So I'm not going to do that myself, but I would like to see that. So we are supporting startups and other companies, even larger companies, who want to do that. And yeah, you said it right. Initially, it was built for research, but it has changed over time, and I really see the opportunity and the potential here for open interface to be used on a commercial scale as well.
So you mentioned mostly then the air interface because we asked questions about that, but you also mentioned that we need a core network. Mm-hmm. And if I understood correctly, the Alliance is also having some projects around 5G core networks. Yes. Can you say something about what are the goals there?
Yes. Yeah, exactly. Open interface provides the whole value chain, let's say. So both the radio elements you need for the radio access network and the elements you need for the core network. The core network is a little bit simpler in the sense that there's no signal processing happening there. So the requirements on the computing is not that high. So naturally, it can run in a virtualized environment on classical hardware. But yes, Open Interface provides, in fact, both the solution for 4G core network and for the 5G core network, or let's say at least the basic elements that allow you to set up the network. There are many things that you can do in the core network, like, for example, we don't provide things like an entity that provides you with billing capabilities. Yeah, that's not interesting for us. But the basic elements to connect the mobile handset to the network are there.
So you mentioned that you are using this in your own research. Can you say something about what you are doing more specifically recently?
So yes, I like you, Emil and Eric, I come from the background of multi-antenna communication. So I did a lot of work on MIMO in my PhD and in my early research days, and I was and I used Open Interface a lot to do research on reciprocity-based massive MIMO. I also did some experimental research on distributed massive MIMO, yeah, more recently the research focus has shifted a bit. These days I'm looking at actually evolving from that from that research. I'm looking at things like positioning and localization in 5G networks, which is something which is very important for especially private 5G networks. I mentioned Industry 4.0 use cases. They want the precise positioning indoors, which you can't really do with equipment that you can with 5G equipment that you can buy today. So I'm looking at how to use 5G networks or the signals in 5G networks to do positioning and localization.
So if we look into the future, then how do you think air interfaces will change over the next 5-10 years, and people who are starting to get involved into research towards future of 5G or 6G, what should they expect is going to change, and is Open Air Interface sort of a research platform also towards the future?
Yes. So I have to say I'm not a very big visionary. So I having a hard time. I had a hard time imagining 5G when people were talking about 4G, and now I'm having a hard time imagining what 6G will be like. But I think it will be more of an evolution than a revolution. And I think, what has been specified for 5G is a solid basis that is extendable also for the next generation. But if I listen to others, then what comes up a lot is artificial intelligence and machine learning. And I think even in 3GPP they have started to create a study item now, how this could be included in the standard. So I think we'll see some of these elements there, and yeah, we definitely 6G will improve on the number of antennas and the processing and some things. And I think that open interface will be also a tool that allows you to do research in that direction.
Mm. Yeah, indeed, very impressive, and found it really interesting to learn more in depth about what you've been up to, and who are really like your main competitor here? I mean, in the space of test beds and let's say platforms that you can, some closed, maybe some open, right?
Yes,
but I mean, obviously there are lots of specialized test beds that have been built for a specific purpose. I'm thinking, for example, of the Lumami test bed that was developed by Lund University in the FP7 Mammoth project to demonstrate reciprocity-based massive MIMO and TDD with spatial multiplexing and all that. And that was built, I think, from mostly USRP equipment, along with some custom-built hardware, of course. Mm-hmm. And then there are also test beds, USRPs to start with, are rather capable, right? I mean, if I understand well, you can connect them together and you can do MIMO and you can do all sorts of things. So from an open air interface perspective, who would you say is your closest or worst competitor?
So let's talk about the software first. So of course there are other projects that use software who implement 3GPP functions or entire base stations in software. I think the most known is Amarisoft, which is also a French company. But their concept is pretty much the same, but their business model is completely different. I mean, it's all closed source, and basically it's a for-profit business who's trying to sell their product to customers. And on the open source side, there are other competitors as well. There is I think it used to be called SRS LTE, but they changed it to SRS RAN because now they also do 5G, which is similar in scope. They use a different open source license. They use a GNU General Public License version 2, I think. And on the core network side, the number of competitors is even higher. There is a project called the 5GC or Open 5GS. I mean, there are plenty that provide core network functionalities in open source. But let's say the distinguishing characteristics of open interface is that it's the only project that is open source end to end. Let's say so from the core network even down to the user equipment. We have implementation of the user equipment too. So it's the most complete, and also, as I mentioned before, it's quite the open source license that we have is quite unique.
Mm. So that's really the unique selling point here, if I understand you well, that you have this openness in terms of the software license, you have this capability of running on general purpose off-the-shelf hardware, and your implementation covers the entire chain. Yes. From the core network down to the air interface, including also device implementations.
Yes, exactly.
Very impressive indeed.
Yeah, really.
Yes.
So do you have any final question, Eric?
I think we could maybe close this up by asking you, Florian, what you think are the most important skills that our students should acquire and learn if they want to be part of, say, the development of the next generation of wireless, which would then be 6G presumably, but I mean, yes. And speaking specifically of the air interface development here that we've been focusing on today. Do you have any thoughts on that?
Yes, I do. So I think as you saw from the discussion, the traditional telecom domain is merging more and more with the classical computer science domain and the cloud computing domain. So if students want to make a contribution to next generation of standards, I think they need to be fluent in both skills. So they need to know how to use cloud-based technologies like containers and things like that. And they also need to understand networking technology and skills of modulation and coding and the different layers of the communication system. So I think that's very important. And of course, if you want to work with open interface, you also need, of course, good coding skills. Yeah, I mean, as I said, everything is written in C, and it's quite some of the functionalities are quite how should I say, use a lot of point arithmetic and very deep,
lots of hacks and tricks
exactly,
to make
deep
it
technology. So you need to be fluent yes. in these programming languages to make a contribution to open interface.
So basically everything spanning from the basic, let's say, math and physics and up to programming in the cloud. Yeah, there's a lot of knowledge indeed that
yes.
the next generation engineers have to acquire. Yes.
Yeah. So is there anything else you would like to take the opportunity to say to our listeners while you're here?
Well, there's just one thing I want to mention. I mean, keep in mind that open interface is a big team effort. So I have been with it for quite a long time, but it was not me who founded it. It was my colleagues Raymond Knopp and Christian Bonnet who founded this. And of course, there were a lot of people along the way who helped developing this. I mean, the community is really large and today, and basically I would like to thank all of them who have made a contribution to open interface. And of course, all the members that financially support the Open Interface Software Alliance that allows us to, keep up the good work and assure the quality of the code.
And thank you very much for joining us for this discussion. And it's really exciting to see how big and successful an open project like this can be.
Indeed, very inspiring. Thanks a lot.
Thank you, Eric. Thank you, Emil. Has been a pleasure. Thank you very much.
Yeah, thank you, and see you in the next episode.
All right.
Bye-bye.
Bye-bye.